Okay, so from 10.4 and on, we will be looking only at testing a series whether they converge or diverge. We will no longer be able to find values of infinite sums in the same way we did it before with the geometric series or the telescoping series. Yes, later when we get to the alternating series test, we will be able but only to estimate values of sums, but not like computing the actual sum like before. Well, you'll see when we get to the alternating series. For now, let's look at one of the easiest, I guess, divergence or convergence test. And this one is called the end term test for divergence. So, we will be given a series sigma n equals 1 or whatever it starts at to infinity of a given sequence. And well, number one, if the limit, so let's highlight with green just to denote convergence, if the limit is a number that is not 0, okay, or if the limit is either infinity or dne, okay, let me write that down, or plus or minus infinity, it could be, that's another situation, then the only thing we will be able to say about the series is that the series diverges. This test is not useful to determine convergence, and if the limit in this case is equal to 0, then the test is inconclusive. Alright? And in that case, we will have to go about a whole different test. So this is, for this chapter, this is the thing, like, we were going to look at a series. Well, after we learned the 10 different tests, and it seems like this test is useful. Okay, we do this test, but for whatever reason, one condition is not satisfied, or we get this limit equal to 0, then we have to look for another different test. All right. Well, let's look at this one. So all we have to do is turn this into a limit problem, find the limit, and from there say whether it converges or diverges based on the value that we get. So limit as n approaches infinity of 2n squared plus 1 over 3n squared minus 1. Well, let's compute the limit. What's the value of that limit? Notice it's an infinite limit with polynomial over polynomial, same degree, numerator, denominator. 2/3. Okay, 2/3. Because this number is not equal to 0, this means that the series converges. No, it converges. Oh, yeah. Never mind. Diverges, yes. Diverges by the nth term test. So it diverges, and in this case we need to specify which test are we using. I know, even though we are in the section concerning to this test, but well, later, like on the exam or something, we need to specify the test. Let's look at the next one. Let's see. So let's turn this into a limit problem. That's a limit n approaches infinity. V to the n squared. All right. So, well, where is this limit going to go as n approaches infinity? Infinity. All right. Infinity or dne, well, depending on the situation. So, for this reason, this is infinity for sure is not equal to 0. All right. And in this case, again, diverges. By the nth term test. Okay. Let's look at the next one. So turn it into a limit problem. Limit n approaches infinity, 1 over 5 n squared plus 3. And well, when we compute this limit to infinity, what's the value? 0. What do we say about 0? Inconclusive. So, well, of course, later in the chapter, we will look for other tools to look at the convergence or divergence of this one. So, inconclusive. Okay, we know what it is. Let's see what's next. All right, how much? Yeah, we have enough time. The integral test. And well, so we're going to use an improper integral to determine the convergence or divergence of a given series. And yes, even though, pretty much every sequence can be represented by some function f of x that we would be tempted to do the integral. In some cases, we can actually integrate those functions. However, there are conditions in order for us to be able to use the integral test. Number one, we can use the integral test if the corresponding function of x is, number one, continuous on the given interval. Number two, it's positive. And most importantly, a decreasing function. Well, here it says on the integral from 1 to infinity because, well, that's typically the indices that we use to represent series from 1 to infinity. But of course, incidentally, we can also use series that go from 2 to infinity, 4 to infinity, well, depending on how those series are represented. And if at least one of these three conditions fails to be met, well, we cannot use the integral test, and therefore we have to find another test. All right? So let's see. And a quick note that we need to be very careful. The value of the integral that we will be computing it's actually not the value of the infinite series. So what we're going to do for this series is use a convergence or divergence of the integral in order to draw a conclusion about the series. So the thing is, if the integral converges, well, then the series converges. But otherwise, the integral diverges, the series diverges as well. All right? So let's have a look at a couple of examples. Let's see. We use the integral test to determine whether the given series converges or diverges. Okay. So number one, before we write an integral, let's write the corresponding function of x. So this series can be represented by the function f of x equals 1 over x squared. So number one, or letter A rather, is this continuous on the given interval? Think of the denominator. Looks like the restricted value is 0. We cannot plug in 0 because, it's undefined. All right? However, is the number 0 within the interval for which the series is carried here? No, so we're good in this case, right? Then this function is continuous. Letter B. Is it positive? Think of every possible outcome by plugging in n equals 1. If we plug in n equals 1, we're going to get a positive number. N equals 2, it's also positive. N equals 5 million, 1 over 5 million squared, it's also a positive number. So it's always positive, which is great. So far, two conditions have met. But number 3, or letter C, decreasing. All right, decreasing. And that's usually the tricky part. If you know the graphs of these parent functions, by heart. Well, that's one way. However, we need to do it the calculus way. So let's see, how do we do this? Number one, so from here, let's take the derivative. So that's f of x, also x to the negative 2, f of x, or f prime equals negative 2, x to the negative 3, which is negative 2 over x cubed. Okay, notice in this case, the derivative will tell us the behavior of the function in terms of whether it's increasing or decreasing. That's the first derivative test. Alright? Back from Calc 1, the first derivative test, if the derivative is positive, well, that's increasing, that we have slopes that are going up the hill. But otherwise, if the derivative is negative, that means that, well, at a given point or an interval, that function will be decreasing, or we will have negative slope. So in this case is decreasing. All right, so we're good. The three conditions are met. So we may go ahead and use the integral test. All right, so the integral from 1 to infinity, and the limits of integration are going to be the same ones as from the infinite series, from 1 to infinity. So that's 1 over x squared dx. And well, recall that to integrate this one, we need to rewrite this in terms of a limit problem. Limit n or x approaches, rather b approaches infinity. That's from 1 to b. That's x to the negative 2 dx. And we can integrate this function using the general power rule. And that's going to be x to the negative 1 over negative 1 from 1 to b. Let's clean up those negatives. Let me write down this negative 1 in the denominator outside of the limit with a negative, simply a negative limit. And this x to the negative 1 as 1 over x. And same limits from 1 to b. That's a negative limit. B approaches infinity of 1 over b minus 1 over 1. But well, where is this 1 over b going to go to as b approaches infinity? 0. And well, 0 minus 1 will be, well, let me write that down. So that's going to be negative 0 minus 1. That's going to be positive 1. Well, that's the value of the integral, right? That's the value of the area under the curve. But that's not what we're trying to find. So what we're trying to find is whether, what we're trying to determine is whether the infinite series converges or diverges based on the convergence or divergence of the integral. So in this case, as a conclusion, as a final conclusion, the integral converges, therefore the series diverges. Oh, wait a minute, no, converges also. Alright, so we have convergence in this case. Alright.